Hello everyone, and welcome to the channel. In this video, we'll take another look at the bus-enabled circuit from the last video, and we'll build a test rig in order to make sure it works properly. I hope you enjoy. Okay, so this is the circuit where we left off in the previous video. There are a couple of small things I want to improve with it before we go on to talk about the ready pin. The first one is I forgot to tie the unused inputs of the NAND gate high. Then we need to set a default value for the bus enable pin if we don't connect it. And for that, I'm going to use a pull-up resistor on the pin. So bus enable is pin 36, and we have it here. I'm just using a 1K resistor for now, but in the final circuit, I'm going to make all my pull-up and pull-downs 10K. The next thing I want to do is if we bring bus enable low, then the CPU is going to put the read-write pin into high impedance, and so we need to set a default value for it as well, because it's connected to our logic, and so we don't want any floating inputs. And so I'm also going to pull it up with a resistor so that the default value is that we are reading, so that we don't have any spurious writes in case we use bus enable. And of course, any DMA system that we use will have to control this pin to access the memory. Now, there are other pins where we need to set default values. The CPU will also put the data pins and their address pins into high impedance, and so we should add pull up or down resistors to those pins so that they are not left floating if we use bus enable. So I'm going to use some more resistor arrays, and let's see how we can do this. So I think I need to redo this circuit a little bit, because I don't have any space to put the pull down resistors on the address pins here. I need to shift this run slot to the right, and I also don't have any space here to add the pull downs to the data pins, nor do I have it here, so I need to do some reorganizing. I think I need to shift this to the right here. It's going to get a bit tight, but it's going to allow me to add a ground line here. Okay, let's do this. So I'm going to have to shift this to the right and redo probably those connections. So let's get started. So this is the pull down on the multiplexed data and bank address pins here. It's going to the ground connection that is here. So the bank address pins I'm actually pulling up through this connection. In the final PCB, I'm going to make this a pull down, but I don't have any convenient grounds here to do it. So it's just going to be a pull up. The high bits of the address I'm pulling down through this connection here. And the low bits of the address, I also don't have any convenient ground, but I do have 5 volts connection here, so it's going to be a pull-up. Again, in the final PCB, I'm going to change this to pull down. Actually, just to be consistent, I'm going to make this a pull-up. So now I just need to bring back all those wires. It's going to be really tight, so I'm actually going to redo them into longer connections. Okay, so now I have our cables. Let's connect them. Okay, so this is everything connected back to it should be. I now have added pull-ups to all the address pins, including the bank address. We already had a pull down on the data pins, so that was good. And I also added pull down to the multiplexed data and bank address pins, as well as the read-write pin. So now any pin that can become high impedance has either a pull down or a pull up. So we're not going to have any floating pin. So let's add our new pull up and pull downs to our schematic. So I have here our KiCad project. Let's see what we can do. So I know I'm going to have to add more pull-ups to some other pins of the CPU, so I'm preparing for that with resistor network. But for now, all those pins are not used. Okay, so I think that looks good. I've added all the pull-down networks to all the address and data pins, and the pull-ups to read, write, and bus enable. And I have some space for future pins that I want to pull up here. Let's go back to the breadboard. So I realize I have connected all of this up so far without actually testing anything. And the reason for that is we can't actually execute code on the CPU until we have some ROM. But still, let's figure out a way of testing all this logic without the CPU. In order to test the circuit, I want to remove the CPU so I can drive all the pins myself. So let's do that. So let's think about what we want to do here. So I want to have two control signals, the clock and bus enable. So I need two buttons for this. Then I want to be able to set the values of the multiplexed data and bank address pins. So I need a 8 wide dip switch. And I really like these dip switches. They fit much better on a breadboard. So these are going to be our outputs, and then we want to be able to visualize what happens at the bank address and at the data bus. So we're going to need a bunch of LEDs. So I'm not actually sure about the color of this. Nor their orientation. We'll have to check that in a minute. So all the LEDs are gonna get 220 ohms resistors through ground. Let's check if I've connected them properly. Here's the power supply. Nope, not the right way around. Actually, I need two. Okay, that should work much better with power. Let's see. Yeah, that's the right way around. And these are orange. So our input is going to be red. The bank address is going to be orange, and the data bus is going to be green. So now we need to connect the deep switch. Okay, so when the dip switch is off, we want the pins connected to ground. And when it's on, we want it connected to 5 volts. So we need pull down resistor here, connected to ground. This is not my best wiring job. And then we need to add power connections to all those pins. Let's try it on. Yep, that works. Okay, so now I should be able to turn on any of the LEDs. Yep, that works. Let's do the same for the buttons. Each button is going to be pulled down to ground and connected to 5 volts on the other side. And let's add an LED for status. So I've talked about those LEDs before. They actually have a built-in resistor. So I connect them directly between 5 volts and ground. Please add current limiting resistors on your LEDs if they are not built in. But I should be able to press the button and turn them on. So the buttons are not actually debounced. I'm going to talk about debouncing when I talk about the clock, but for now it should work fine. Let's see. This button is going to be bus enable. The bus enable is on the top here. And this button is going to be the clock. These are going to be our multiplex data pins. And now I need to connect the outputs of those chips. Finally, I need to connect power between those two boards. And there we go. Let's see. So unfortunately, I just realized that we need another signal, which is read-write. And I don't have any more space here, so I need to move all of this a bit to the right. That's unfortunate. C'est la vie. Okay, so let's check if I've broken anything. Should be able to turn on the LEDs. Did I flip it? Yep. So that's still good. Let's add another button. Okay, so in yellow, this is going to be our read-write signal. And it defaults to low, which means we are writing. Actually, I just realized I don't actually need buttons for read-write and for bus enable. I just need the one for the clock. Let's tie bus enable high, because we want to check that case first. And then let's tie read-write low, because the write cycle is easier to reason about. So currently the clock is low. We are in the latching phase. So anything that we put on the multiplexed data pins should be reflected directly on the bank address, because the latch is transparent. And when I bring the clock high, this data should be latched, and then it should appear on the data pins. So let's see. Okay. And now I can change what's driving the data pins. But the latched bank address will stay here. And now if I release the clock, this will, the data pins buffer will be reset to 0, and then latch will open, and this will appear in the bank address. There you go. Now I can latch this value again and change the data. And if I let go of the clock, then this goes back to 0, and the latch becomes transparent. Awesome. Now what happens with bus enable going low? It's pretty simple. It's just a default value. So as I said before, I added a pull-up on the bank address and a pull-down on the data bus. And so now I can turn on and off the clock, and nothing will change because the output is disabled. But the latch will still work. It will still hold on to data. So let's see. Now it has latched this value. So if I change it, now hold on. So if I turn on the clock, then it will latch this value, and I can change the inputs. And if I turn on the bus enable again, this one, you can see that the previous value has been latched, and you can still access it, even if I turn off and on the data bus. Okay, so the circuit in write cycle seems to be working fine. It's more difficult to actually test the circuit in a read cycle. So we need to switch which part of the test rig is actually driving the bus. So when the clock is low, we need to be driving it from here, but when the clock is high, we need to be driving it from the output side. So it's more difficult to test. But based on the behavior in a write cycle, I'm pretty confident that the circuit will work properly. So let's unplug this and go back to our main circuit. And we can reinstall the CPU. All right. So in the next video, we'll take a look at how to use the ready pin to stop the CPU during DMA access and how it impacts our latching circuit. So I hope you enjoyed this one. Let me know in the comments if you have any comments or feedback. And I hope to see you in the next one. Goodbye.